Something bigger than just a new electric vehicle model is emerging. Beneath all the usual talk about range and acceleration lies the core of the revolution, the battery. Lithium-ion technology has powered the first chapter of electrification, taking us this far, but carrying significant drawbacks, fire risks, capacity loss over time, and supply chain challenges. Tesla's new aluminum-ion battery, set for release in 2026, marks the start of an entirely new chapter. This technology prioritizes safety by essentially eliminating fire hazards and offers endurance that outlasts the vehicle itself. The real competition has shifted from who builds the fastest car to who earns trust through reliable, safe battery performance in the toughest conditions, whether scorching heat, freezing cold, or long, rugged drives. Tesla's aluminum-ion battery completely removes the fire risk inherent in lithium-ion packs. Traditional lithium-ion batteries rely on flammable liquid electrolytes that pose a constant danger of ignition in overheating or impact scenarios. In contrast, Tesla's design uses a pure aluminum core that benefits from naturally superior heat resistance. While lithium-ion batteries become risky at temperatures above about 120 degrees Celsius, aluminum-ion batteries function safely up to 200 to 250 degrees Celsius, nearly doubling the thermal safety margin. A revolutionary feature of Tesla's battery is its aluminum cathode superstructure, introduced in late 2024. Unlike the flat, sealed cathodes in lithium systems, this cathode is crafted as a honeycomb lattice made of thousands of tiny hexagonal units. This 3D honeycomb increases the surface area five-fold and disperses heat roughly 40 times faster than lithium cathodes, allowing the aluminum battery to cool itself effectively and prevent overheating hazards. The surface is further enhanced with a nanoscale ceramic coating only about 0.5 micrometers thick, thinner than a human hair, that smooths the cathode surface for even ion flow, preventing energy traffic jams that can cause hot spots and explosions. This advanced structure also eradicates dendrites, the tiny metal spikes that commonly grow inside lithium cells, puncturing separators and causing short circuits and fires. Aluminum-ion batteries do not form dendrites, eliminating the industry's most dangerous failure mode. Without the need for bulky cooling systems or heavy protective shells, the battery pack itself acts as the safety mechanism, cutting out risk at its source and providing unprecedented peace of mind for drivers. In practical terms, the fire risk with Tesla's aluminum-ion batteries is cut by over 99%, even under severe stress like overheating or intense collisions. This is particularly critical for drivers in extremely hot areas such as Arizona, Death Valley, Florida, and Texas, where ambient temperatures routinely soar. While lithium-ion batteries can exceed 90 degrees to 100 degrees Celsius and risk swelling, sparking, and catching fire, aluminum-ion batteries stay below 60 degrees Celsius, fully blocking these hazards. Tesla's crash testing shows aluminum-ion battery fire risk falls to 0.05%, roughly 50 times safer than traditional lithium-ion batteries, which carry a 2.5% fire risk in similar crashes. Unlike lithium cells that release flammable electrolytes and spark chain reactions under impact, aluminum cells remain stable, warm slightly, and safely contain any damage. The design also focuses on pack-level safety. Every micromodule inside the battery is wrapped in a thin aerospace-grade barrier that prevents heat transfer and directs vented gases through dual exhaust channels. In case of cell failure, which is chemically unlikely but still possible, microfuses trigger in 4 to 6 milliseconds to cut off current flow and isolate the fault before heat can spread. Tesla's abuse tests showed that even with nail punctures, peak temperatures stayed below ignition thresholds, and no thermal propagation to neighboring cells occurred. Tesla's battery pack acts as its own firewall due to the efficient heat management of the aluminum honeycomb cathode and ceramic surface. In trials with cells overcharged at high ambient temperatures, no adjacent modules exceeded 45 degrees Celsius, and thermal propagation was completely suppressed. By contrast, lithium-ion packs rely on bulky liquid cooling and heavy armor to try to achieve similar safety, often with less success. Controlled venting further enhances safety. Without volatile carbonate solvents, Aluminum-ion cells vent less than 8 liters of gas per second in the worst case, releasing it downward beneath the vehicle. This drastically reduces harmful gases like carbon monoxide and volatile organic compounds inside the cabin, maintaining visibility and breathable air, giving occupants more time to evacuate safely. To prevent fire risks from electrical faults after crashes, Tesla equipped the pack with ultra-fast isolation switches that reduce voltage below 60 volts within 10 milliseconds of a crash sensor trigger. Combined with arc-proof bus bars and gel-filled feed-throughs, this nearly eliminates ignition sources from post-impact electrical arcs. SLED tests estimate post-crash fire risk at just 0.03 to 0.06%, making these the safest packs ever tested. Everyday impacts such as road debris, tow hook mistakes, or curb strikes are mitigated by a tough skin tray that spreads out puncture forces and reduces local strain. In high-speed underbody tests, internal temperatures rose less than 12 degrees Celsius, and the pack quickly recovered operation after isolating the damaged area. This turns potential hazards into manageable maintenance issues, greatly enhancing daily safety for vehicle owners. Beyond safety, Tesla's aluminum-ion battery achieves unprecedented longevity. Current lithium-ion batteries in EVs like the Model 3 and Model Y tend to lose capacity significantly after 300,000 to 500,000 miles. From 80% capacity, they degrade towards 50% over the next 100,000 miles. Tesla's aluminum-ion battery, however, is engineered for a lifespan of 3 million miles, enough to last the lifetime of multiple cars. This is possible because aluminum-ion batteries use gel polymer electrolytes with extremely high boiling points, around 300 degrees Celsius, that do not evaporate or break down like lithium carbonate solvents. These solvents create solid deposits on electrodes over time, blocking ion flow and reducing battery life in lithium designs. Furthermore, the new chemistry allows ultra-fast charging at currents up to 100 C. This quiet revolution in battery chemistry means vehicles equipped with these packs could drive for over 200 years at average American usage, 7 to 11 times longer than current top EV battery lifespans. This will change how people think about battery replacement, resale value, and the total cost of vehicle ownership. As safety removes the main obstacle of fires, economics and regulations transform accordingly, opening the door for aluminum-ion and other non-flammable chemistries to replace lithium-ion batteries, whose market share is projected to drop from over 90% today to less than 50% by 2030. This evolution in battery technology, from fire hazards to near-perfect safety, from limited longevity to multi-million-mile life, and from costly logistics to streamlined economics, marks a fundamental change in transportation. Tesla's aluminum-ion battery technology doesn't just improve electric vehicles. It redefines how the world powers transport, making it safer, longer-lasting, and more affordable for everyone on the road.